Now let me good morning again, everyone. Let me now I'm going to introduce derivation of loop gain and the stability test for robot automatic Biquad filter. In this work, we show our research background in the first part, and in this talk, we emphasize on the this difference between the conventional loop gain and the repose shallow function in a transfer function. And we also saw some methods to define the transfer function and the shallow function in a multi-shot system. In the second part, we just show a simple second order transfer function, and we investigate the behavior of the phase machine of the shallow function in a second order system. And we also show some phase machine of the basic ideal of M network. Moreover, in practical design of two-stage FM, we also discussed some effects of the Muller capacitor, and we show our experimental result in part 3, and the final, and we conclude our talk in the part 4. The motivation of this work. As you know, the ranging occurs in both passive and active network, or in both feedback and without feedback system. The ranging is an unwanted oscillation of a voltage or current, and that we call extra current flow. So that's make your device very high heat there, and then it can affect in the input port and the output port of a system. In some case, the overshoot will make your measurement machine work in saturation region. So in this work, we will investigate the behavior of a high order active networks, especially in the op-amp connection. And we just show the behavior of a second order low pass automatic Biquad low-pass filter, because the active low-pass filter are used in many applications. They can design in differential topology or in complex filter. So if you don't know well the behavior of a second order active network, it's very difficult for us to optimize the third order, the fourth order, or higher order low-pass filter. And as you know, that's the complex function. Why in this work we emphasize on the behavior of a complex function, because the conventional theory neglect stability test. We use the polar chart to investigate the stability of a network. But from the property of the complex function, we can express the behavior of a complex function in both complex plane or in the spectrum domain. So we can express their property are not changed, and we can investigate. We can investigate the behavior of a network using body plots, or we combine the magnitude frequency, the angular frequency plots into one magnitude angular diagram. And in this work, we want to clarify the difference between the conventional loop gain and the repose shallow function. Why? In a general transfer function, we can measure the transfer function by the ratio between the output signal over the input signal. in another word, we can express a general transfer function by A of omega over 1 plus L of omega. In this case, L of omega is the scalar function. When the denominator go to when the denominator is equal to 0, it means that the system is unstable. And we in this work we use the concept of phase machine to investigate the behavior of high order complex function. And you know that in the conventional theory, especially in control theory, the concept of a negative feedback network is only used in the switching DC to DC converter or in two-stage op-amp. But when we can express the behavior of a transfer function when we define the concept of a scalar function, so the behavior of a negative feedback system is the same as the behavior of a transfer function. In this work, we focus on the stability test at the output nodes in an analog system, because when the incident current is greater than the transmitted current, this can call the overshoot. And now let me recall the first method to derive the scalar function. As you know, in practical measurement, the open loop gain of an op-amp is very high. So in simulation, we can derive easily when we measure the scalar function. We measure the open loop function, the transfer function, and then we derive the scalar function. In another way, if we want to verify or we want to check the behavior of an open loop function, we can measure the scalar function, and then we measure the transfer function, and after that we can define the behavior of an open loop function. So in this work, we try to emphasize on the alternating current conversation, because it can be used in simulation or in practical measurement. And the basic concept is the incident current is equal to the transmitted current. And now the scalar function is defined by L of omega is equal to minus the incident voltage over the transmitted voltage. And now in this work we also use a passive balloon transformer to measure the scalar function in a design of Thomas robot filter. Now, because the objective of this work, we will use the second order Thomas to robot filter to design a complex filter in a row IF transceiver. So when we want to define the transfer function of a complex function, it's very difficult for us to use the conventional methods, because we have to consider the effect of each shot in a network. We have to separate them and remove a signal source by another network, and without affecting the final result. And so with the simple circuits, we can do easily, but in a complex network, this method, the conventional method, is painful experiments. And you know that I think all of you know that the conventional middle roof methods we can define the loop gain of an adaptive feedback network, especially the switching DC to DC converter. But how about the high order active robot filter? This method is not acceptable. And the conventional replica measurement, we have to use two identical circuits to derive the shallow function of a network. So this method is not accepted in practical measurement. And the conventional Nyquist stability test, this theorem is only used in theoretical analysis for feedback system. And in some case, you can see that the conventional concept, the analysis and the measurement of loop gain are not unique. Therefore, in this work, we try to emphasize on the shallow function of a second order transfer function. Now, let me summarize behavior of a second order transfer function. And on the summarized table of the behavior of a second order shallow function, we can see the phase margin at the unity gain of the shallow function is 76.3. In case of overdamping, the phase margin is very high, and in case of underdamping, the phase margin is very small. Now let me show a simple case of a second order system. In this case, when the system operates in underdamping region, the phase margin at unity gain is 52 degrees, and in time domain you can see the overshoot occurs. And now let me review shortly the behavior of an ideal op-amp. In this work, we design an ideal op-amp as a 10 megahertz gain bandwidth and 100,000 DC gain. And it's easy to define the open loop function and the shallow function of an ideal op-amp. And you can see that at the unity gain of the shallow function of an ideal op-amp, the phase margin is 90 degrees. It means that this system is absolutely stable. Now let me review some basic op-amp networks. The op-amp can be used in the inverting op-amp connection or in the buffer connection. And in the conventional method, you can approximate the DC gain of this network by the ratio between minus I2 over I1. But how about the shallow function of this networks? In this result, we saw the shallow function like this. And we also define the shallow function in case of a buffer like this. Now, let me clarify the difference between the conventional loop gain and the repose shallow function. The conventional loop gain is used to define the reduction of between the DC gain of an ideal of the op-amp to the design gain. We can design we can use op-amp at a different gain, and we can, if we reduce the DC gain, we can increase the bandwidth of a network. And in case of a buffer, we can see that the gain is 0 dB, and the gain bandwidth does not change in on case. now let me show the behavior of the transfer function in the repole networks. And from the body's plot of the cellular function, we can see that at the unity gain of this network, the phase machine are the same, 90 degrees. It means that these networks are stable. But in practical design, the parasitic capacitor, resistor, or when we lay out a chip, the parasitic component will match your your design, and will match your design chain and significantly. And now, in case of without frequency compensation, we can simplify the second state of this op-amp like this. And in case of with frequency compensation, we can simplify the second state of this op-amp like this. Now let us define the transfer function of the second state in case of without frequency compensation. After applying the superposition principle, we can see that the transfer function of this network is second order. And in case of with frequency compensation, we can see that now the transfer function and the cellular function are fourth order complex function. So the behavior of this network is extremely complex. And to investigate the behavior of the design to state op-amp, now we can simplify this model like this. And in this work, we use the buffer connection or the buffer topology to investigate the behavior of the mirror capacitor. And the simplified model like this. In case of underdamping region, you can see that the overshoot occur in case of underdamping. And at the cutoff frequency, you can see the gain is very high. And if you design a very large mirror capacitor, and the rising time is very slow. And now let me show the phase machine in case of underdamping region. The phase machine is very small. At unity gain, you can see that the phase machine is about 10 degrees. And next, let us review shortly the behavior of a second order tau biquad networks. After applying the superposition at every node, we can define the transfer function and the cellular function. And in simulation, we use the voltage shot to define the cellular function in this network. In calculation, in hand calculation, we can investigate the behavior of a second order tau biquad and robot filter by the chosen component. And in simulation, we can see the body plot of the transfer function at the cutoff frequency. They are 90 degrees. So the transfer function cannot be used to investigate the stability of the system. And now let me show the behavior of the cellular function in the second order tau robot filter. At the unity gain, you can see that in case of underdamping region, the phase machine is 45 degrees. And now let me compare the measurement result to the theoretical analysis. We also use a 10 millihenry passive balloon transformer to measure the solar function in the implemented circuit. Now, let me show the phase machine at the unity gain in case of underdamping region. We can see that the phase machine is 30 degrees, and on the body flux of the transfer function, and at the cutoff frequency, the gain is 20 dB. This gain will amplify the high order harmonics of the input signal, and that's called damp oscillation noise, or that make the ringing. Now let us summarize our work. In this talk, we review some property of the complex function and the behavior of some basic op-amp network, and we also show the application of the repose methods to measure the solar function in the implemented circuit. And if the phase machine is smaller than 76.3 degrees, this system is unstable, and we have to investigate the behavior of the parasitic component in this system. In future work, we will clarify the repose method in high order complex filter. That's all for my talk. Thank you for your kind attention.